So, welcome to the final week of the course Introduction to Data Science. So, the purpose of this course actually was pretty basic, in order to have all of you on the same line. Next course, we will do all the multivariate methods. That is, principal components, discriminant analysis, cluster analysis, and then we will have the so-called devices. So you'll be given an Arduino device, and then you will be asked to measure, for example, pollution or other things with this device. You can put this device at home, so you can remotely control it. For example, if you want that the heater system starts in a particular time, these things are quite expensive, but if you know how to program them with 2 lines of code in MATLAB, this is quite easy. And we will see all these advanced things in the second course. Now, thanks to all those who wrote in the issues and provided suggestions. And do not forget during the exam to write your GitHub nickname. And do not forget to mention that you have or not your name in the page of errata corrige, in the page of the corrections, right? So do not forget to let me know whether you have or not your name in the page of errata corrige. Everyone knows that there is this file, okay? So if you have your name here, and the rules of the game are, if you have your name here, +1 for every report. If you have on the other end your name here, +1/3 to your final mark, right? These are the rules of the game, right? So if you have 3 reports on the first section, +3, it is clear that if a person has participated, and then I enjoyed very much, and then I answer to all the people who participate. So I have to discriminate those who participate from those who do not care anything at all. So please do participate, because I will keep into account your participation. And your participation remains when you are in front of a firm and then they tell you, are you in GitHub? And they, yes, this is my nickname and this is what I've done. Right? Everything which is on GitHub remains for all your life. And now, you see, this is type on page 149. You understand it. In the first center, there is, you need not wait. This is not clear to me. Not clear to me what you mean. If someone maybe can help me to understand what CCAR BSS. Yeah? But yeah, but in page 149. Here. Or at least let me know, I mean, which line you are talking about. This seems to me a bit vague. Yes, please tell him, because he is right, but I mean, if he tells you 149, you need not wait. This is something that I cannot understand. So if someone can help, I will be very happy. And You remember that 15 days ago I had told you that it will be a very good thing to put the clickable legend in the polar histogram? This has been done because this is our group of people. So if you think you'd like to have inside FSTA a particular function which is not present, given that we are not software users, we are software developers. So your teacher is not one plus one of the millions of users. Your teacher is a software developer, right? I wanted to be one of those who makes the future. No, of course, I will not make it. That goes without saying. But at least so, if you wish to have a particular function, okay, let us know, right? Then there is the auto-completion in polar histogram. Therefore, let me tell you what I mean. So, when you compute a polar histogram plot, okay, now you see that the legends are clickable. And if you now see this Italy, you see that there is the auto-completion. You see that these things appear, right? Before they did not appear. Now the suggestions appear. Data vars, for example, 1, 3, and that's it, right? Or then there is 1, 3, and then, for example, display style, and then with the auto-completion, everything appears. For example, bars or stairs. No, bars, stairs, okay, and then this is the option with stairs. Okay. Now, so remember to be, if you want to be notified for all the activities, remember in the GitHub to check this option. Now, November, good morning. Now, November the 18th. I don't know if you received did you receive an email? Okay. So, this is a webinar which is organized by 5 departments of the University of Parma, because, of course, they all use MATLAB. And so there is a link in order to join the event. It is not necessary to be, a sort of preliminary registration, no, not at all. So the first talks will be in Italian, but the last talk will be in English. But, you know, these are all people, you see, for example, this is a sort of portfolio analyst. He has a very important position. So if you maybe show up, ask a question, maybe you are likely to be considered. Maybe in this, in this big tech asset management, we are talking about, investment funds. We are talking about millions of euros. Therefore, try to attend, try to show up. In life, you have chances. Try to exploit these chances, right? Or, for example, here there is the second one is the European Commission. The European Commission as a series of positions for stagiaires. And these are the persons who are responsible. Francesca Torti and Domenico Perrotta are the co-developers of FSTA. So, given that you already know the basics and even more, try to show up and then to try to ask questions. Of course, they manage English, their language is English, or this person that can even manage French as a PhD in the École Supérieure de Lyon. So, all these people can manage any language. So this is, for example, Sidel. Sidel is a sort of Coca-Cola company. Some Coca-Cola company. They do with bottle filling, and so they have developed a series of apps in order to make sure that the bottle is perfectly cleaned. We are talking about 100,000 of bottles, and then all of them must be clean. You can imagine the damage that you get if one bottle is not perfectly cleaned. And so they use MATLAB in order to do all these things. An additional incentive is that those who attend get +1 to the final mark. When you attend, make sure that you attend with the credentials of the University of Parma, right? Otherwise, I cannot trace you. So make sure that you log in with the University of Parma credentials. Otherwise, I cannot track your participation, right? Otherwise, I see guest and I don't see your name. So everything you can imagine, everything that then at the end of the webinar, there is automatic list of participation. I mean, those each person, the time he has logged in and the time he has logged out, he or she has logged out. So remember, November the 18th. Okay, this is the end of now of the remark, and now we can move to the course. So we are dealing with the contingency table. We are dealing with the contingency table of size capital I times capital J. In this case, capital I is 3 and capital J is 4. So here there are 4 Italian regions. There is toothpaste and there is A, B, and C. There is a commercial, own brand B, or brands available in numerous shops or indifferent. Well, because it is important to understand whether the consumers of a particular region consume a toothpaste of type A or type B or type C. In other words, there is a connection, there is a relationship, an association between A, B, and C and the region, yes or not? What is the theoretical frequency that I expect here if the two variables are independent? It is clear that in order to make a test, I have to compute the theoretical frequencies under independence. Then I have to compare my actual frequencies with those that we have under independence. So this is the original contingency table with the generic capital I rows and with generic capital J columns when the variables are independent. The variables are independent if the probability of observing xi does not depend on y. The fact that y was equal to y1, the fact that you are here, or the fact that y was equal to y2, or y was equal to capital J, does not matter, because these probabilities are exactly the same as the marginal probabilities. You see what independence means? The presence of a particular value of y does not matter. And then you observe y or you do not observe, is the same. It's the same thing. So, or these conditional probabilities are equal to the marginal probabilities. Therefore, asymptotically, because this is a sample, and of course sample values are not equal to the asymptotic values. Asymptotically, this is what we expect. Okay. If there is this set of equalities, then we have a formula in order to compute Nij. Nij is equal to Ni dot times N dot J divided by N. You see the point? You see why under independence Nij should be equal to this guy here times this guy divided by N. You see, is that. And therefore, independent if and only if this, there is this chain of relationship, and this therefore Nij is equal to this, the product of the margin divided by N. And this is what we were trying to do in the past lab section, right? So, in case of independence, then you have a formula in order to compute Nij star. Now, first of all, you may wonder, how do I generate a contingency table in MATLAB? For example, yes, I wanted to have a contingency table with with 3 rows and 5 columns. Okay, clearly, or you do it with okay, also here we generate contingency table with size 3 times 5. Okay, and then okay, run contingency table, but you want to do it with a particular formula, of course. Well, the copilot is always there to generate a contingency table once and for all. This is fine. And there is this function rcontfs, which is one of the functions of FSTA, generates a random two-way table with given marginal totals. In other words, so, well, if you type the name of the function, then you have the link, and then you go to the HTML page of the function, where there is all the explanation of this function. And then you can see the example. For example, here it says, I want to have a contingency table in such a way that you have 2 rows. The marginal frequencies of these 2 rows are respectively 20 and 30, the marginal frequencies of the rows. Then you have 3 columns, and the marginal frequencies of the columns are 25, 15, and 10. So, sample size is 50, right? Let us see. Or you can see all the output here already. So you can see now that there is the constraint 25, 15, and 10. You see 25, 15, and 10 for the columns. You see the constraint for the sum of the rows 20 and 30. So 20 the sum of these numbers, and 30 the sum of these numbers. And then you have 2 algorithms for creating contingency table, right? Therefore, using this function, you can specify the number of rows, the number of columns, and the marginals for the rows and for the columns, right? So, but this is true for any function of FSTA. Here there is the full documentation. Now we have to compute the theoretical frequencies, and then we have to compute the chi-square test. Chi-square test, double sum. So you check the difference between empirical and theoretical square, and then divided by the empirical. Okay. If the null hypothesis of independence is true, if there is independence, do you expect small or large values of this statistic if the independence hypothesis is true? Sample values tend to population values, right? So if there is independence, you expect that more or less the difference between Nij and Nij star is small. So you expect that this statistic, which has values in the interval 0 plus infinity, because it's sum of squares, so of course cannot be negative, you expect that the value of the statistic is small, vice versa. If the alternative hypothesis is true, you expect that these differences are large. But what large means? A value of 20 is large, a value of 35 is large. This test statistic has a distribution. The distribution under H naught, under independence, is chi-square with these degrees of freedom. A capital I minus 1 times capital J minus 1. Why this number here? Well, let us consider, for example, this contingency table. If the margins are fixed here, 99, if I have 49 and 16, number 34 is given because the marginal is fixed, right? So if these numbers here are fixed, if you have here 0 and 0, automatically here you have 99. Similarly, if here you have 222, these numbers can be chosen as you like. Okay, well, but the sum of these three numbers must be smaller than 222, cannot be larger, because the total of the row is fixed. But if the numbers of these three is 200, then this number automatically must be 22. So you have capital I minus 1 degrees of freedom for the rows and capital J minus 1 degrees of freedom for the columns. That's why you have this formula here for the degrees of freedom. Hi. Okay. Now, this value of the index depends on the sample size, in the sense that if you multiply by 10 this number, also this number is multiplied by 10, and this number is multiplied by 10. So what happens to the index if you multiply your contingency table by 10. The index remains the same, not at all, because you have the square, so it's multiplied by 10. So multiplication by Q, all the values of the contingency table, if you multiply them by Q, chi-square is multiplied by Q. So depends on the sample size. If this thing depends on the sample size, n, what do? You divide it by the sample size. That's obvious. Depends on something, divided by something. And then you take the square root. Well, if you take the square root, then this index lies between -1 and 1. If the contingency table is 2 times 2, but it's not in the interval 0, 1. If you have more than 2 rows or more than 2 columns, in order, if you have an index which is in between 0 and 5, what do to make it stay between 0 and 1? If you end it divided by 5, this goes without saying. And so here you divide it by the maximum. That's the reason, yes. So you take the former index and you divide it by the maximum. If you divide it by the maximum, you have the so-called Kramer index. So the interpretation of the Kramer index is very clear. If it is 0.3, the association is 30% of the maximum possible value. Right? Okay, now the distribution of the statistic is chi-square. Chi-square random variable is well known. So we know the quantile. You know what is the value which leaves on the right a proportion, a probability of alpha. And then, given that you know this quantity, the value which leaves on the right a probability of a quantile, the quantile 1 minus alpha, therefore the value which leaves on the left a probability of 1 minus alpha, and to the right a probability of alpha. Okay, so you choose alpha, a small value, and then if the result of the test is greater, than the quantile, okay, then you reject, because your the result of the test has a small chance if the independence hypothesis is true. Now I want to know whether you want me to implement these things online. Okay, so we do the code together, or this is very obvious and then everything is absolutely clear and then we can skip it. Which option would you like? Okay, well. So it is clear what we are going to do in the next 5 minutes. In the next 5 minutes, we are going to have contingency table, then we are going to compute the theoretical frequencies, and then we are going to compute the value of the chi-square test, right? From scratch. This is, unfortunately, this is what you want me to do. So, for example, well, so we start with the contingency table. Okay, let us call it, I call it N table. So, then let me put a seed, RNG 100, so we save the file, ptmp, and then run. Okay, so I fixed the seed, so we always have the same contingency table. right? So I have n. Now I want to extract just the numbers from this table. I extract just the numbers. Okay. So n is the contingency table just with the numbers, not in table format. Now, compute matrix of theoretical frequencies. Frequencies under independence. Well, you know, the artificial intelligence, even if I put here, there was a typo, automatically here he has written the code. You see? Then I even think that they can record your voice. This is what, because yes, because otherwise certain things, but they surely record your voice. Yes, this goes without saying. Even if your mobile then is switched off, it is clear that Google can listen what you are saying. This is absolutely very, very clear, and must be known to all of you. At least, okay. So you now, well, this is the matrix of expected frequency. But let me see. This is correct, right? Yeah. Well, you know. So I have. You know the formula here. This is the formula. So in general, so therefore this is what the artificial intelligence does. And this is, but of course, I can do it much more efficiently in this way. So sum n 2 is here the sum of the rows. Sum n1 is the sum of the columns. So if I do 3 times 1 plus 1 times 4, what do I have? 3 times 4, right, where the generic entry is the ith element of this column vector times the jth element of this column vector, right? Therefore, the ij entry is this, divided by total sample size. Total sample size. Total sample size that well, a human would write it this way, sum n all. Right. So you see, this is the implementation of this formula here. For each I and each j, the matrix of expected frequency, Nij divided by n, right? So therefore, these are the frequencies that I expect. I expect 116. On the other end, what do I observe? I observe 54, then I observe 85, and then this is the matrix of expected frequency. 85, and here what do you observe? 91. Now, the difference between the numbers which are here and the numbers which are here are large or are small? Now we have to implement the chi-square index. And let us see how the artificial intelligence implements it. Ok, compute the chi-square index. Let us see. Yes, the artificial intelligence automatically, okay, this index is well known, and automatically this is the implementation. So you see, in matrix form, without loops, so each element, we accept it, each element of n minus each element of this one. You see that square, each element is square, and then each element is divided by the expected frequency. And then, well, this is a matrix. This is a matrix, right? And now you sum all these elements. You see sum all. Tell me, in MATLAB, how is it possible that a person does not reach the target? It's impossible. It's impossible. Tell me, how is it possible that a person does not compute this index? I mean, so this is clearly, of course, this is the top software with top, I mean, that when you type it, then automatically you write it in English and then automatically gives you the output, of course, but if you know the theory, then the implementation is nothing. Or compute a chi-square index, so you see this is the chi-square statistic. Chi-square statistics 386. Okay. This quantity here is distributed as a chi-square with capital I minus 1 times capital J minus 1 degrees of freedom. Let me see. Oh, look, degrees of freedom of the contingency table, because I really want to see. Incredible. N row is defined. N row. N row is n column. Right. They were defined here. Yes. And so these are degrees of freedom. That instead of writing n row, we write I, shift enter, and capital J, shift enter, so that everything is renamed capital I, capital J. Run. Okay, the degrees of freedom are 8. And then look how you can immediately see that it has been generated by the AI. You look at the spacing. There is exactly a space here, a space here, a space here. So it is incredible, because if it is perfect, it is clear that it has been generated by AI. Yes. Now, degrees of freedom. Now, compute. No, okay. Well, now it is amazing, because now it has, I didn't even have to put that I wanted to find the p-value, because he anticipated me. So if you think in a certain way, then automatically the code comes along. So I want to get the p-value of the chi-square statistic. Right. I want to have the probability. What is the probability of observing a value which is greater than chi2 stat? And the p-value is 0. The p-value is 0, therefore this is a contingency table taken from internet. Who knows, God only knows where he took this contingency table. And then in this contingency table, I surely reject the null hypothesis of independence. The p-value is 0. So the differences between expected frequencies and real frequencies is significant. And in fact, you see, 54, you were expecting, so this was, let me see, this 54, and then 57, and then let us see the second. 85, we had 45. Now, now what we do? Okay, now we compute the Kramer index, right? So we compute the Kramer index. Therefore, we compute this quantity, phi, chi-square, the value of the chi-square divided by m in square root. Compute phi index. Incredible, eh? Yes, because in the literature it's called phi index. So he knows, right, the value of the chi-square divided by m, the square root. Right, which is exactly this formula here. You see, the value is square root of chi-square divided by n. Now, you take this phi index, let's say phi index. If you want to be fancy, you call it phi, not phi. If you want to be Greek, then you call it phi. If you want to be, in Italy we say fighetto, you call it phi index. Now, compute Kramer index. What can I say? Now, what can I say? Yes? Isn't it amazing? Tell me. So, therefore, is, well, but this is, let us do it, this is phi index. Therefore, is phi. Well, yes, this is true, but it is phi index divided by the square root of the minimum of I minus 1 and j minus 1. So you see, the phi index, because it has already been computed. Here it has computed it from, scratch, but you already had computed phi index, so you use the phi index. So it's phi index divided by the square root of minimum I minus 1 and j minus 1, right? Okay. So the Kramer 0.36. The association is something like 37% of the maximum possible value, right? Tell me, is high. There is what is the entry barrier to this? 0. What is the entry barrier to do these things? Do you agree with me? Is 0.00001. Okay, right. And then you know that version 20 and 26A, this is the version that I'm using, the pre-release, because you know I want always to be at the cutting edge, so I always wanted to test the most recent version, the version that people will be using in 2 or 3 months ago, in 2 or 3 months time. So, but you all, with the license of the University of Parma, can download the pre-release, and then you do whatever you like. Okay. Now, here inside toothpaste, this exercise, the data are inside the file toothpaste. Let me see. So toothpaste. So first we check this file. Okay. So you have toothpaste region. This is a survey, and then to each person it has been asked, which is the toothpaste that you use, kind A, B, or C, and then which region do you come from, because that was a project in order to understand whether to create a new firm in which region. So you want to understand if the consumers of a particular region are more keen in consuming a particular brand of toothpaste. Right. So you read the file. Let me put my layout markup. So you read the file. Okay. So this is therefore this is the original. You see that I call it X. Let me first of all do close all and clear all, because I have in the workspace I have many variables. Okay, so data loading. Toothpaste. Okay. So this is the data matrix. Then I want to know whether you solved this issue or not. So, okay. There is an association between the first column and the second column. Shall we close it? She wants to say something. Okay, so you see that Cuban supernova is this is her nickname in GitHub. Is really a supernova, right? Now I'm happy that we have created let us say a joking way, and this is how you have to learn statistics, not to be too serious. No, in fact, when I leave home in the morning, then my wife says, "Please be very serious with the students. Do not say jokes." Well, and then when I come back home, then my wife says, "But you have done anything during all the day. It is clear now. Come on the other end, I did this, I did that. On the other end, you stayed quiet, relaxed, and seated, talking to your students. This is the most easy thing in the world." Okay, I will stop it. And now I keep going. So, function crosstab is an old function of MATLAB. Then it has been going on for 20 years. This function has 4 outputs. So you supply the 2 variables, and then it computes the contingency table. In non-table format, it computes the value of the chi-square, it computes the p-values, and these are the labels for the rows and the labels for the columns of the contingency table. Right, then you have to do array to table in order to create your table. Then you take the dimension, then you do array to table, and then you display your table. So now, the value of the chi-square is 403, the p-value is virtually 0. No way. In Italy, it is clear that people who come from different regions have habits which are significantly different. In the future, there will be less and less, but this survey took place something like 10 years ago, and 10 years ago there was significant evidence. Now probably things are changing, are evolving. Then here there is, you see, the manual implementation, manual chi-squared, manual implementation of the p-value of the Kramer index. Now, let us say probably what in the modern version of MATLAB, what do you do? Given that you have this X, you compute the pivot table. You compute the pivot table directly, so you don't have to pass to array to table, so just compute the pivot table and that's it. So here there is manual implementation, the phi and v. Now suppose, because people now are getting lazier and lazier. So here what you want to have, you have your file, you want to have just one line of code that computes everything. So you have your file, one line of code, and that's it. This is what you want to do. For example, you have this sparkling wine here. Sparkling wine here, you want to check what is the relationship between taste and food pairing. You know, in fact, there is really, unfortunately, a big difference between certain areas of the world where we keep care of these two variables when there are much more serious problems in other parts of the world. Because you see, because we have so-called vinitaly. Vinitaly, where all the wine producers go there, and so they want to understand what is the taste, and then the taste of the wine which goes together with what? The food pairing. So this is the food pairing and this is the taste. Now, therefore, or it's same thing, you do read the table and then you do pivot. Read the table, you do pivot, and then you have this contingency table. Now, you want to have just one function which does it all, does everything, right? So you have core nominal of n table, and then you put the result into out, does it all, right? Does it all. This is the FSTA function that we have written, so it computes the chi-square, the p-value, the phi index, the Kramer's v, 56. The association is a little bit smaller than 60% of the maximum possible value. Then you have, this is the Kramer v, then you test the null hypothesis that the Kramer v is 0 and the p-value is absolutely 0, so the correlation, the association is significant. And then here you have even a confidence limit, a confidence interval, because these are sample values. So you have an interval which contains, with the prefixed probability, in this case 95%, the true value of the index. So in the sample, you have observed the Kramer v, which is 0.56. These are the set, the range of population values, likely population values. And the confidence interval does not include the value 0. So 0 is not a value which is likely value. Therefore, you do reject one more time the null hypothesis of independence, right? So here it says that the true value of the index is in the interval 0.4, 0.67. The true relationship, association between these two variables is in between 0.4 and 0.67. Now we are going to see all the other indexes. But at least here you want to have the pivot. But there are people who are even more lazy, that don't even want to compute the pivot table. Given the file, they want to do everything with just one line. Okay, so given x, then you can do core nominal. If you have this option, then you say, look that this is a data matrix, these two variables, this is a data matrix, gusto, gusto, this is the Italian wine, this was taste, right, and then abbinamento, that was food pairing, right. So if you do this thing here, you automatically have everything. You see everything. At least you have to do read the table, at least, and you have to do read the table to load your data into MATLAB. Once you have loaded your data into MATLAB, then you call core nominal, but they say, look, this is not an input, it's not a contingency table. The input is a data matrix. Right. Then there is also option which is called plots and is equal to 1. Now, let me know if you think that it's important to have the auto-completion, because writing the auto-completion takes time. But however, if you say that it is important to have the auto-completion, we are going to do it. For example, let's do with plots is equal to 1. Plots is equal to 1, then it automatically generates, does all the computations as before, but it automatically produces 2 additional plots. Because, you know, the chi-square index, the chi-square index here, you see, written in LaTeX, the chi-square index here is the sum of all these quantities, double sum for I and j. Therefore, here, I know that, for example, the overall statistic is significant, but you want to see the contribution to the chi-square index of each combination of I, which combination of j. You see the point? Therefore, here it says that sweet and dessert, sweet wine goes together with the dessert in a frequency which is positive and then much larger than you would expect under the independence hypothesis. Is it clear? Similarly, for example, aperitif and fish with sweet, well, sweet wine does not go well with fish, of course. And so the frequency here is negative. That is, okay, this plus minus because the sign is the sign of Nij minus Nij star. Because it is clear that it is a square, so the square, it is clear that it can just be positive. In order to trick the cards, in order to have the square which is positive or negative, then you supply the sign of Nij minus Nij star. Okay, this is imperfect style of FSTA with the legends which are clickable. And then here you have the Pareto plot. The Pareto plot says, what are the 3 combinations which make the 80% of the overall chi-square index? And then you immediately see them. So you see, right, this is the interpretation that a statistician wants to have. Not just the value of the overall index, but the contribution of the single ingredients which make up the overall index. Well, this so far we have been unable to make all this legend, also this legend clickable. So far, we have not been able to do it. Okay, now you see that there are other indexes here. Now we are going to explore the other indexes. Therefore, first you test whether the relationship is significant. Just if the relationship is significant, then you compute the Kramer indexes and the other index, but just if the association is significant. Now, index is based on error reduction. This is another set of indexes for contingency tables. Okay, so let us recall the interpretation of Kramer index. So if the Kramer index, which is an index which goes in between 0 and 1, if it is 0.3, okay, the association is 30% of the maximum possible value. But however, this index does not have an underlying probabilistic model inside. Okay, let us now see indexes which have a probabilistic model. Now you see that this is the type of degree, and this is the output. Here it says that among the 1,000 persons, there are 150 which were graduated in economics that work for the private sector. And here it says that there are 50 that were graduated in economics that were still unemployed. Now, you may ask, and this is the total. The total here, well, assuming that you do not know the kind of degree. The idea is, let us compute 2 errors. The errors that you make if you know what is X, and if you don't know what is X, right? So your goal is predicting Y. Your goal is predicting Y. Your goal is predicting whether a person will work for private, public, profession, will be a professional, or unfortunately will be unemployed. Then, you know the degree or you do not know the degree. That's the thing. And then, okay, so if you do not know the degree, you don't know these values. So you simply know the values which are in the last row. You don't know X. Now, what is your prediction if you just know the values which are in the final row of the table? What a sensible person will predict. And what is the error? The error that you have. If you just know these numbers here, And then they tell you, what is the most likely outcome? The most likely outcome is what? The most likely outcome is public sector. But what is the error that you make? Tell me. What is the error that you make in the long run? What is the error? Okay, the 380 divided by 1000, and the error is 0.62, right? Is it clear? Now, GOM. Okay, now suppose that you know that you are dealing with a person who graduated in economics. You know that you are dealing with a person who comes from economics. You just know the numbers which are on the top row. What is the probability of error in this case? Which is 0.5 probably, yes. Yeah, well, probability goes between 0 and 1, right? Yes, however, it's 0.5, right? Yes. And okay, now you know that you are dealing with a person that graduated in humanities. What do you forecast? What is your forecast?
Not good.
Not good, yes. No, okay, you got it. Your forecast is not good. Okay, but you make a mistake. And the mistake you make is with probability 80 divided by 200, right? So you see the probability of error of case 1 and then probability of error of case 2. So if you, the probability of error of case 2, but okay, if you know, this is your favorable cases are 150, 250, 120. So the probability of error becomes 0.48. The idea is that you compare these two numbers. Very, very simple. And so this is a very probabilistic framework. This is the probability of error in case 1, 0.62. You just know the bottom row, or each time you know that particular row. And this is the index, which is called lambda proportional reduction error index of Goodman and Kruskal. Is an index which is in between 0 and 1, is an index which is not symmetric, and the larger is the index, the greater is the predictive dependence. So a very simple interpretation, an index which lies in between 0 and 1. Remember that the index is not symmetric, so it can be here probably you don't even need MATLAB to compute this index. So if this index is 0.2258, okay, the probability in predicting this sector by knowing the type of degree is 0.22, a gain of 22.58%. So you see, it has very simple to compute and then gain in interpretation. But this has led to a battery or set of indices that are called on the proportional reduction of heterogeneity. What is heterogeneity? Probably you already know. If you have, let us say, a frequency distribution, and then, we call variability the differences between the values of a phenomenon which is measured with numbers, quantitative or quantitative, you can pronounce it as you like. Or heterogeneity deals with the differences between the categories of a categorical phenomenon. And then here, intuitively, what is the situation of perfect homogeneity? Perfect homogeneity, of course, it goes without saying that you have something like that. All the frequencies are zero, and then there is one frequency which does it all. Right. Perfect, on the other hand, perfect heterogeneity is what? So if you have just 3 levels, 33% each. If you have 4 levels, 25% each. So this is the case of maximum heterogeneity. All your frequencies are 1 divided by p. Well, these are 2 extreme cases, and now there are indexes which are called the indexes of heterogeneity that want to understand, are you close to this case, closer to this case, or are you closer to this case? Right? So there is, this famous Italian Gini, and there is this Gini index. And then, or standardized Gini index, so you divide it by the maximum, and so you get an index which goes in the interval 0, 1. This is what statisticians do. An index has a range, you divide it by the maximum, and so you get an index which is in the interval 0, 1. And then you have the other entropy index. I don't know if you already heard these indexes. So the idea, therefore, is compute this index in the marginal distribution of y, here, or compute this index in the ith row. Then you do the sum, and then so you see if knowing I is important or not. If this index computed in the last row is equal to the index computed in the ith row, knowing the ith row does not help as before. You see the point? So you compute the index for this value here, and then you compute the index for the first row, for the second row, for the ith row, the capital ith row. And then the index computed here is different from the index computed knowing that x is equal to x2. That's the idea. And so is index of the heterogeneity based on the marginal frequencies of y, or based on a particular row of the contingency table. Well, you have these indexes which are called h and tau, and then their formula is terrible. Well, I've always refused to learn it by heart. No, absolutely. But no. But you have to understand that they exist. They measure the reduction of heterogeneity. So now, sparkling core nominal. Nominal when you do one well, actually we had already computed them. These are the 2 indexes. So you see they're very similar. The indexes which are in the interval 0, 1. This is the test null hypothesis that the index is 0. And then you can see that there are different indices, but they all give you the same information. So you see the p-value of the null hypothesis, that the value of the index is 0, is 0. And then here you have, for example, their confidence interval, but all of them suggest that 0 is not inside the confidence interval. Therefore, gk lambda yx is the Goodman and classical index that we have seen about the forecast of the sector given the degree. These are the two other indexes, which are index of reduction of heterogeneity using Gini index or Shannon index. This is what you have to know. However, you see, therefore, the summary is that core nominal does it all. Okay? Function of core nominal. Okay, and now the interpretation. So, for example, if this is 0.35, a reduction in heterogeneity or in Shannon heterogeneity. Once again, if the confidence interval of the index does not contain 0, this is the sign that 0 is not a likely value. And then this with the plots option. Well, this is something that we have already seen, and then the association now for ordinal variables. So far, you saw the name core nominal. So the name core nominal came out from a brainstorming among the FSTA group. So core nominal is correlation for nominal variables. Now you will have core ordinal, that is contingency table, but where there is an order. Because so far, the order, the fact that a person was graduate in economics, in arts, so you could switch the rows, you could switch the columns. Now, for the ordinal, no, you cannot do it. Right? So, here, there is an association between the mark in the two exams or not. And what is the degree of association between the two marks? So you see the difference with what we saw before. Okay, now we have to introduce the so-called concordant pairs and number and discordant pairs. Let me see. So, of course, when a pair is concordant, a pair, I mean, you have two students, they produce a concordant pairs. They produce concordant pairs if the students with higher value of x also got a higher value for y. So suppose this is a sort of written oral exam. Therefore, if you have these 20 students who got sufficient and sufficient, they are concordant with other which other students? They are concordant with those who got more in the two exams. So 20 is concordant with 45 because these 45 people got fair and fair, more and more. They are concordant with fair and good because good was greater than sufficient, fair was greater than sufficient, so they are concordant. They got a higher mark in the two exams. And they are concordant with 15. So 20 is also concordant with 15 because they were better in the two exams. And fair is 40, is concordant with what? We got more and more. 40 is concordant with 45 and 15, right. And 45 is concordant with what? 15. So you see, these are all the calculations. Can you see them? The number of concordant pairs, right? So the number of concordant pairs is 5,475, right? Now, what are the number of discordant pairs? Those who get sufficient and fair are discordant with what? First exam, sufficient. Second exam, fair. Greater, eh? They are discordant with what? And 0. Right. And 0 even more. Even more. Because, yes, now 0, yes. And 20 is discordant with what? With this 4. So this is the number of discordant pairs. So the rule is that concordant below on the right, discordant below on the left. Right. Okay, now you have to implement it in MATLAB. Right. So we, as usual, we do it together. 5 minutes, okay. And there will be one time where you tell me. Doesn't do it. So let me see if it copies it into Word or whatever. Yes, in Word it copies the table. And now if I put it in MATLAB, yes, you see, if copy and paste directly from PowerPoint does not work, you copy it into Word and then from Word to MATLAB it works. Contingency table. Okay. This does not, at least this time, it has done something that I don't, oh well, we can keep it, but I don't know. Let us see, because this concordant paired compute the number of concordant pairs, because that's difficult, eh? At least it has done something, eh? It has initialized the number of concordant pairs, eh? Right. Concordant pairs that we call it, we call it capital C, right? C is equal to 0. Vediamo un po'. Use a for loop, a double for loop. I hope that it does not do it. Eh? I use a double for loop in order to compute C. You mean that, well, this is scary, because now I want to check. I want to check if the result is correct. Now, just let me see. I wanted to check if the result is correct. Let me run it. See? Ah, no, fortunately it is not correct, because the result should be 5,475. Fortunately, maybe in 2 or 3 years' time it will be able to compute. Fortunately. However, it is true that we can obtain something, you know, the structure, the for loops, so let us try to do it. For example, ij is equal size n. Therefore, now, in order to compute concordant pairs, 20, which is here, is concordant with what? None, because you cannot have more than good, right? Therefore, your loop goes from I is equal to, and from j is equal to, here, correct, I minus 1, and then j, and j. So I have, you see, I have to do it for 20, for 40, for 10, and for 45. So I goes from 1 to capital I minus 1, and j, same thing, right? Okay? Yes, because no one is greater than the last row. No one is greater than the last column. This goes without saying. So here it is C is equal to the previous C plus Nij times Nij times C, Nij plus times the sum of n, which indexes?
From I to the last I.
No, not I.
From I plus 1.
Right. From I plus 1 up to capital I, and then
J plus 1.
up to,
J minus 1.
no, capital J. You see, 20 is 1, 1, so from 2 to 3, and in this case from 2 to 3. So 20, the sum of this block down here. So ij plus the sum, and then sum all. This matrix, you sum all the elements. Right? Okay, now let us see the debug. And so save tmp whatever, and now we are here. Run. And now there is the debugging. First stage, C is equal to what? Is equal to 0. Let us check. Then Nij in the first stage is what? Now you are I is equal to 1 and j is equal to 1. Then you have Nij is what? 20. You see, and now you check it. Evaluate selection, you see, it is 20, Nij. 20 times this matrix here, times this matrix here, times the sum of the elements of this matrix. And now we check it. Yes. I plus 1 up to capital I, j plus 1 up to capital J, which were these four, Right. You see, these four here. This 45, this 4 here. You see? And so, when you do this thing, what you have? That C is equal to 2200. 2200, therefore, is this computation here. And now you check it. 2200 is this computation here. Yes, 2200. 5. Then, step, what you have now? That j now is equal to 2. J is equal to 2, step, and no. Well, it has, one moment, let me run it. Step, and j is equal to 2 now. J is equal to 2. So, C is equal to 2200. Then you have this thing here. You have that I and j. Now I is equal to 1 and j is equal to 2. Therefore, this value here is 40. Let us check it. 40. 40 times 60. The sum of 45 plus 15. So you see the sum of these matrix here. And you see 45 and 15. The sum of these elements. So, therefore, you just check all this. This is equal to 2400. 2400, which is this thing here. 40 times 60. So now you add these two. Now C, which was equal to 2200, you add 2400, and so you get 4600. Okay, now remember that j from 1 to j minus 1, therefore step, then it gets out of the loop, and then where it goes, now with I is equal to 2. With I is equal to 2. With I is equal to 2, and j now is equal to 1. So now you are dealing with I is equal to 2 and j is equal to 1. So you are dealing with the number 10. Let us see if it is true. Number 10, yes. I is equal to 2 and j is equal to 1. Number 10, you have to add 10 times 20. You see it? See, 10 times 20. 10 times 20. And then let us see if this matrix here is the matrix that we want. Yes, 5 and 15. Because when we are talking about 10, greater and greater is 5 and 15. And the sum is what? The sum is 20. The sum is 20. So what do? You add to the sum, 10 times 20, so you add 200. You add 200 here. So you have to check that this is 200. So you add 200. Now I is equal to 2 and j is equal to 2. This is the final thing. J is equal to 2 and I is equal to 2. So Nij is 45, this one, times 15. This one must be 15. Yes. Step, and then you go out. Your C is 5,475, which is exactly this. What is the difficulty? Maybe before it was 0.001. Maybe now it is, if you want, 0.1. Yes, maybe, well, it has not been at least something where the machine does not automatically generate it, otherwise we go away. Otherwise, my wife is fully correct. Say, why are you going to teach the students? Okay, thank you. So see you in yes, around in 20 minutes, 25 minutes, right?